Hi everyone, welcome to Algebra 2, Chapter 7, Lesson 6, the natural base e. In this video, we're going to discuss e as a number, how to graph an exponential function with the base e, and natural logarithms. So let's take a look at what e is. So e is a number, and like pi, e is an irrational number that's approximately equal to 2.7182818. I know it looks like there is a pattern there, but it is not. It is irrational. It is approximated by this function here, f of x equals 1 plus 1 over x to the x. As x gets large, the value of the function will approach e. Notice what I did is I put it into my graphing calculator, and I set the table to go really high, really fast. So you can see this is kind of a little far away from what we want, but notice as I scrolled down, the 1 stayed here, and then I got a 7 here. If I keep scrolling, this 7 will eventually turn to an 8. So it will eventually, as you scroll down, get to this number up here. Let's take a look at how to graph an exponential equation where e is our base. In example 1, we're asked to graph the exponential equation, f of x equals e to the x plus 2. So the first thing that we would do is create a table of values. I always pick a few negative numbers, 0, and a few positive numbers. That way, if anything unique happens, I'll be able to catch it in my graph. So all I did was I took a calculator, I did e to the negative 3 plus 2, e to the negative 2 plus 2, and I got all of these numbers down here. Now all I need to do is put them on a graph. So notice on my graph, it has the same general shape as an exponential function, but notice this is a vertical translation up 2. So my horizontal asymptote has moved up to y equals 2. So that's how you graph an exponential function. I always make a table of values and then graph those points. Let's take a look at what a natural logarithm is. The natural logarithm is a logarithm of base e. So e is the base on the log. Now, it is abbreviated as ln, and you do have an ln button on your calculator. If you have a TI-84, it would be the third one up from on. And we don't actually write it as log base e. That is implied when you see the ln. Now, natural logarithms have the same properties as logarithms with other bases. So the product property, quotient property, power property, and a lot of those other inverse properties will work with this. So just like with regular logarithms, this is an inverse function for e to the x. So natural log x is the inverse of e to the x. Domain and range of this logarithmic function is that our x values have to be greater than 0. Our range is all real numbers. Let's take a look at applying some of the properties of logarithms to natural logs and exponential functions with the base of e. So we've been asked to simplify each expression. We have natural log of e to the negative 2t. We have e to the natural log of t minus 1. We have e to the 5 times the natural log of x. So I'd recommend pausing the video and trying to simplify those and then pressing play, or you can just keep the video running. This first expression actually equals the negative 2t because this is a log base e, and the base matches this exponential expression right here. So I'm saying e to what power is e to the negative 2t. So the e's cancel out, you just get negative 2t. In part B, we have e to the natural log of t minus 1. Now remember, this is log base e. So again, the e and the log base e will cancel out. So you're just left with t minus 1. In part C, I have to apply the power properties of logarithms where this 5 becomes the power on the x. So I moved that there. Now e and the natural log will cancel out, and you're just left with x to the 5th. Now let's take a look at some applications of exponential functions with the base of e. The first application we have is continuously compounded interest. So the general formula for that is that the final amount equals the principal, which is the initial amount, times e, which is our special number for the lesson, times the rate of interest. Now that rate has to be changed to a decimal number. It's usually given as a percentage. okay? And then it's times the time that it is staying in this situation. Usually time is given in years. So let's take a look at an example question where we have to apply this formula. In example 3, it says, what is the total amount for an investment of $1,000 invested at 5% for 10 years compounded continuously? So what we're going to do is take these numbers and put them into our formula. 1,000 is the original amount, so that's the P, the principal. 5% is the interest rate, so we change that to 0.05. And 10 years is the time, so I'm going to put that in the time area. So here's my filled in formula, and I just typed this into my calculator, and I got $1,648.72. And I did round it for money. We're talking about money, so you would round to the hundredths place. Okay, the other application we're going to talk about is half-life. So half-life is what happens when a radioactive material decays to half the amount that it originally was. So let's say I start with 100 grams of uranium. Half-life is the amount of time it takes for that 100 grams to turn into 50 grams. So the equation for this that we use is N of T, which is the amount remaining, equals N sub 0, which is the initial amount, times E to the negative, don't miss the negative sign, that means it's decay. K is the decay constant, which will change based on whatever material you're using, times T, which is time. So with this equation, we can figure out first the decay constant, then we can figure out the time that it would take for it to reach a certain amount. Let's take a look at an example to hopefully make this a little more clear. In this example, we're asked to determine how long it will take for 650 milligrams of a sample of chromium-51, which has a half-life of about 28 days, to decay to 200 milligrams. So the first thing we're going to do is find the decay constant. What I usually do is I pick an initial amount that's easy to work with, like 100, and then I do half of it over here, 50, because we know the half-life is 28 days. So if I put in 50, 100, E, I don't know the K, but I do know T is 28, I can then solve that equation. So I'll show you how to do that first. So I filled in those numbers. I just divided by 100 to get half, which makes sense because it's half-life. I did a natural log on both sides to get rid of this E, and you're allowed to do that on both sides. Then I got rid of the E using the properties of logarithms, and I just divided by 28, the negative 28. And I got K is about 0.0248. Now the rounding on this is really important. You want to keep a lot of decimal places, at least 4. You can do more than that, probably not less than that. Now in step 2, we're going to solve for T. So I'm going to take the 650 and 200, put it into the equation with my K, and find out how long it takes. You'll notice these steps are very similar to the steps I did in part 1. I divided by the 650. I did the natural log on both sides. The natural log and E canceled out. And then I divided by this negative 0.0248. So T is the natural log of 200 over 650. And I hit enter on that in my calculator. Then I hit divided by this negative number. And I got about 47.5 days. So that's it for this video. Make sure you let me know if you have any questions.